Good morning, students. This is Arvind, Assistant Professor, Department of EEE, DBS Kavali. So in the previous class, I started switching converter series compensators. So in that class, I discussed about the TSSC and the transmitted power versus transient angle characteristics. And now in this class, I'm going to discuss the control range and VA rating of the switching converter series compensators. And next, I'm going to discuss the capability to provide the real power, to exchange the real power, or capability to provide the real power. Like that, those concepts I will discuss. Firstly, I will start with the control range and VA rating. Okay. So, in the TSSC can provide capacitive or inductive compensating voltage. Okay, you know already this one. The TSSC can provide capacitive or inductive compensating voltage independent of the line current up to its specified current rate. Okay, so thus in voltage compensation mode, the TSSC can maintain the rated capacitive or inductive compensating voltage in face of changing line current theoretically in the total operating range of 0 to IQ maximum. That is illustrated in this diagram. So actually, this diagram gives the attainable VA characteristics of the TSSC when operated in voltage control mode and reactance control mode and the associated loss versus line current characteristics. Okay, so firstly I will discuss the first diagram, that is A1 diagram. So this is the attainable VA characteristics of the TSSC when operated in voltage control mode. Okay, that is A1. So the current theoretical total operating range of 0 that is to IQ maximum, that is illustrated in the figure A1. Then the corresponding loss versus percent of the rating of the TSSC versus line current characteristic is shown in the A2 diagram, that is this one. Okay, on the left side we have two diagrams, one is at the top and one is at the bottom. Okay, so in those two diagrams, the VA rating of the TSSC is simply the product of maximum line current and the maximum series compensating voltage. VA is equal to I maximum into VQ maximum. Okay. So coming to the third diagram, that is B1 diagram. Okay. So in this one, in impedance compensation mode, the TSSC is established to maintain the maximum rated capacitive or compensating reactance at any line current up to the rated maximum. That is illustrated in the diagram B1, that is on the right side top diagram. Okay, so the corresponding loss versus line current characteristic is also shown in the 6.35 B2 diagram, that is in the bottom of the right side we have B2 diagram. Okay, so note that in practical applications, as indicated previously, for variable impedance type compensators, okay, I maximum may be separately defined for the rated maximum steady state line current and for a specified short duration over current. Okay, so the basic VA rating of the major power component of the TSSC must be rated for these currents and for the relevant maximum voltages. So it is shown in the figure 6.35. Okay, that is in the previous class I discussed about 6.35 diagram. So that and TSSC of 1.0 per unit, VA rating covers a control range corresponding to 2 per unit compensating watts. So that is the control range is continuous from minus 1.0 per unit, that is capacitive watts, to plus 1.0 per unit, that is inductive watts. So in many practical applications, only capacitive series line compensation is required. That means minus 1 per unit is required. Okay, so in these applications as well as in those which are already used or plan to use series capacitors as part of the overall series compensation scheme, the TSSC may be combined cost effectively with a fixed capacitor, that is FC, that is illustrated in the diagram, this one, figure 6.36. So this is the hybrid compensation scheme, that is a combination of the TSSC with fixed capacitor. So this is the hybrid compensation scheme consisting of a 0.5 per unit for fixed capacitor and 0.5 per unit for TSSC. Okay. So where and TSSC of 0.5 per unit, VA rating is combined with the fixed capacitor of 0.5 per unit. So in this one we have SSSC. So it consists of 0.5 per unit, and the fixed capacity also consists of 0.5 per unit. Okay, so BAC rating to form a continuously controllable overall series capacitor with a maximum compensating range of 0 to 1 per unit capacitor. So the injected voltage versus line current characteristic of the SSSC plus fixed capacitor arrangement in the voltage compensation mode is shown in this diagram, that is 6.37. That is 6.37. So in this one we have attainable same. It is replicable to the 6.35 diagram. So in that one also we take an attainable VA characteristics of the SSSC, that is for the hybrid series compensator. So in this one we are using hybrid series compensator, that means combination of SSSC plus fixed capacitor. So in the previous diagram we discussed about the attainable VA characteristics of the series compensation, normal series compensation operated in voltage control and reactance control, and the corresponding loss versus line current characteristics A1, A2 and B1, B2. Okay, so the injected voltage versus line current and characteristics of the SSSC plus FC arrangement in the voltage compensation mode is shown in the 6.37 A1, and in impedance compensation mode, that is in the B1. So one is for the voltage compensation mode and another is for the impedance or reactance compensation mode. So that is A1 and B1, and A2 and B2 gives the corresponding loss versus current characteristics of those things. Okay. So the corresponding loss versus line current characteristics are shown in the 6.37 A2 and B2, that is below diagrams of the quadrant diagrams of the left side and right side diagrams. Okay. So this compensation scheme from the standpoints of major component, that is converter and fixed capacitor ratings and operating losses, is extremely advantageous in spite of the fact that the fixed capacitor produces a compensating voltage that is proportional to the line current, and therefore the controllable compensating voltage range of the overall compensator also becomes to some degree a function of the line current. Okay, so that is the concept of control range and VA rating of the SSSC. And next we are going to next topic, that is capability to provide real power compensation. The capability to provide real power compensation. So in contrast to the series compensator, that is series capacitor, which functions in the transmission circuit as a reactive impedance and as such is only able to exchange reactive power. So the SSSC can negotiate both reactive and reactive power of the AC system simply by controlling the angular position of the injected voltage with respect to the line current. So however, as explained previously, the exchange of active power requires, that means real power, the exchange of real power requires that the DC terminal of the SSSC converter be coupled to an energy source or sink or a portable energy storage. Okay, so the capability of the SSSC to exchange real power has significant application potential. Okay, so one important application is the simultaneous compensation of both the reactive and resistive components of the series line impedance in order to keep the X by R ratio high. X by R ratio means reactance to resistance ratio is high. So in many applications, particularly at transmission voltage levels of 115, 230 and even 340 kV, where the X by R ratio is usually relatively low, that is in the range of 3 to 10. So a high degree of series capacity compensation could further reduce the effective reactive to resistive line impedance ratio to such low values at which the progressively increasing reactive power demand of the line and the associated line losses and possible voltage deflections would start to limit the transmittable active power. Okay. So this situation is illustrated with a phasor diagram in figure. For a normal angle control line whose uncompensated X by R ratio is 7.4. So that is this one, this diagram. So this diagram gives the limitations of line resistance on power transmission increase by series capacitive compensation. So in this one we have the circuit diagram and phasor diagram. So in this one, the XYR ratio is changing from 1.85 to 7.4. So that means X effective by R, that is equal to 1.85, and X effective by R, that is 3.7, and XL by R, that is 7.4. That is 0 to 75% we are taking. So we are 0% and we are 50% and we are 75%. So at that time, Vx, that is R is equal to 0, and Vx effective, that is 0%, and Vx effective is 50%, and Vx effective is 75%. Okay, like that we are taking. And we have the currents from 0 to 75, that is R is equal to 0 and 0% to 75% we are taking, and the angle also alternating, that is 0% to 75%. So in this one we are taking two machine system, each consisting of a transmission line. It consists of a resistor, inductor and capacitor. Okay, so here the combination of the resistor and the combination of the inductor and capacitor reactance is the effective reactance, and voltages are the Vx effective. So as seen by applying increasing series capacitive compensation, that is example 50 and 75%, the effective X by R ratio decreases to 3.7 and 1.85 respectively. From this diagram I explained. Okay, so as a result, the reactive component of the line current, that is I sin of delta by 2 plus phi, supplied by the receiving end system progressively increases, and the real component, that is I cos of delta by 2 plus phi, transmitted to the receiving end progressively decreases with respect to those which would be obtained with an ideal reactive line, that is R is equal to 0. I am explaining about these dotted lines. Okay, that is R is equal to 0, that is 0 to 70% currents, line currents, and the transmittable active power P and the reactive power Q supplied by the receiving end bus can be expressed for this simple two machine system, employing angle adjustment for power flow control at constant and voltages, that is Vs is equal to VR is equal to V, as functions of the reactive line impedance, the line resistance R and function angle delta as follows, that is P is equal to V square by X square plus R square of X sin delta minus R of 1 minus cos delta, and Q is equal to V square by X square plus R square into R of sin delta plus X of 1 minus cos delta. These are treated as 6.16 and 6.17 equations. So next, so the normalized active power P and reactive power Q versus angle delta transmission characteristics described by these two equations, that is 6.16 and 6.17, are plotted as a parametric function of the X by R ratio for X by R is equal to infinity 7.4, 3.7 and 1.85 in figure, that is 6.3, and that is this diagram. Okay, here the characteristic diagram is drawn between real power and reactive power versus load angle delta. So here the delta is variable from 0 to 180 degrees, and the XL by R ratio is between now infinity to 1.85. So here the thick curves real power and the dotted lines gives the reactive power curves. Okay, so here the diagram, the circuit is the same as we seen in the previous diagram, same diagram we are taking, but here we are not considering the capacitor. Okay, so here, so these plots clearly show that the maximum transferable active power decreases and the ratio of active to reactive power increases. So these plots gives so that maximum transferable active power is decreases, and what is increasing here, the X by R ratio is increasing here. Okay, the triple C with an appropriate DC power supply. Okay, the triple C with an appropriate DC power supply would be able to inject, in addition to the reactive compensating voltage, a component of voltage in antiphase with that developed across the line resistance to counteract the effect of resistive voltage drop on the power transmission. Okay, in this way, by providing simultaneous and independently controllable compensation of both the reactive and real impedance of the line, in effect an ideal reactive line can be created for maximum power transmission. So it should be noted that the power, that is I square R, would of course still be dissipated by the physical line. So however, this dissipated power will be replenished by the TSSC from the auxiliary power supply. So the real power compensation capability could also be used effectively in minimizing loop power flows by balancing both the real and reactive power flows of parallel lines. So next, so the recordings obtained from the PNA simulation of a two-machine system compensated with the TSSC with the DC power supply, that is this one. So actually, the same diagram we already seen in the previous class by using the oscillogram from PNA simulation showing the capability of the TSSC to provide the both. Actually, in that one we only have reactive compensation. In this one we are giving real and reactive compensation with the series line compensation. So that is plotted. So the recordings obtained from a TNA simulation of a two-machine system compensated with a TSSC with a DC power supply illustrated the combined compensation of the line reactance and resistance. Okay, so the plots show the line current I in phase A together with the corresponding receiving end, that is I minus N voltage, that is VR is equal to V2, that is this one. I V2. In the first one we have phase A and we have the line current I and V2. Okay, so the waveforms is like that, in no compensation and capacitive compensation and capacitor and reactive compensation we have like these waveforms. Okay, so in this one the transmitted power P together with the reactive power Q, that is supplied by the receiving end. Okay, PQ, that is supplied by the receiving end. And next, the line current I again in phase A together with the voltage VQ that is injected by the TSSC, that is third waveform, that is IVQ injected phase A. Okay, that is supplied by the TSSC, and the active and reactive power the TSSC exchanged to the AC system via the series voltage injection for no compensation, purely reactive compensation, reactive Q plus resistive compensation, that is for the last diagram. Okay, so these are the four waveforms. One is supplied by the transmitted power, that means we are receiving end, and another one is for the supplied by the line current, and another one is supplied by the TSSC, and another one is supplied by the combination of reactive and real resistor compensation. Okay, so next, so it can be observed that the additional resistor compensation increases the transmitted power significantly, while it also decreases the reactive power demand on the receiving end. So from the standpoint of dynamic system stability, reactive line compensation combined with simultaneous active power exchange can also enhance power oscillation damping. So for example, during the periods of angular acceleration, the TSSC with a suitable energy storage can apply maximum capacitive line compensation to increase the transmitted active power and concurrently observe active power to provide the effect of damping resistor in series with the line. So during the periods of angular acceleration, the TSSC can execute opposite compensating actions, that is, apply maximum inductive compensation to decrease the transmitted active power and concurrently provide the effect of negative resistance to supply additional active power for the line, that is the negative damping. Okay, so there is the one more concept, and we have another concept, that is immunity to subsynchronous resonance, that is SSR, immunity to subsynchronous resonance. So the desired function of the series capacitor is to provide a compensating voltage opposite to the which develops across the reactive line impedance at the fundamental system frequency to increase the transmitted power. Okay, the desired function of the series capacitor is to provide a compensating voltage opposite to that which develops across the reactive line impedance at the fundamental system frequency to increase the transmitted power. So however, the impedance of the series capacitor is a function of frequency, and thus it can cause resonances at various subsynchronous frequencies with other reactive impedances present in the network. Okay, as discussed in the previous section, in recent years there has been considerable progress made in modifying the inherent frequency characteristic of the series capacitor in the dominant subsynchronous frequency band by a parallel connected transistor control reactor, that is TCR, making it immune to subsynchronous resonance with the use of electronic control. Okay, so in contrast to a series capacitor in an impedance type series compensator, the voltage source converter is a static synchronous series compensator. Okay, the TSSC is essentially an AC voltage source which with a constant DC voltage and fixed control inputs would operate only at the selected output frequency, and its output impedance at other frequencies would theoretically be zero. So in practice, the TSSC does have a relatively small inductive output impedance provided by the leakage inductance of the series insertion transformer. So the voltage drop across this impedance is automatically compensated at the fundamental frequency when the TSSC provides capacitive line compensation. So thus the effective output impedance versus frequency characteristic of the TSSC, operated at a constant DC voltage remains that of a small inductor at all but its fundamental operating frequency. So consequently, such an TSSC is unable to form a classical series resonant circuit with the inductive line impedance to initiate subsynchronous system oscillations. So in the practical TSSC, the voltage source converter on the DC side is terminated by the finite energy storage capacitor to maintain the desired DC operating voltage. So thus the DC capacitor in effect interacts with the AC system via the operating switch array of the converter. Okay, so this interaction may conceivably influence the subsynchronous behavior of a practical TSSC. So for the purpose of this discussion, let it be assumed that the TSSC has no source or sink of power attached to its DC terminals, and furthermore, let us neglect the power losses of the converter. So the DC terminal voltage is thus supported entirely by a DC capacitor bank. So with perfectly balanced sinusoidal line current, the converter will produce balanced sinusoidal voltages in quadrature with the line current, and the DC capacitor bank will experience no charging current since no real power is exchanged at the AC terminal of the converter. So if the converter is controlled to produce these same voltages while additional sub and super synchronous components are introduced into the line current, then alternating power components will appear at the AC terminals of the converter, and these will be matched by alternating charging currents in the DC capacitor, producing in turn an associated alternating voltage component on the capacitor. So this is because the energy transfer through the converter is absolutely direct, and thus the net instantaneous power at the input terminal must always be equal to the net instantaneous power at the output terminals. Okay. So for example, if the line current contains sub and super synchronous components with frequencies of f sub, that is the frequency of subsynchronous is equal to f0 minus f1, and super synchronous frequency is equal to f0 plus f1 respectively. So in addition to the synchronous component of frequency, that is f0, due to the modulation process taking place at the mechanical system frequency, that is Fm, during the subsynchronous resonance stipulated in the example. So then an AC current component of frequency, that is Fm, will flow through the DC terminals to balance the fluctuating power appearing at the AC terminals of the converter. So as a result, the DC terminal voltage of the TSSC converter will have a superimposed AC component with frequency Fm. So if the converter control ignores this AC component, okay, so that is if it is operated to produce the AC output voltage as if the DC terminal voltage was constant, then the TSSC will have sub and super synchronous voltage components in its output with the same F sub is equal to F naught minus Fm, and F super synchronous is equal to F naught plus Fm frequencies. So however, it should be recognized that the variation in DC link voltage does not inherently affect the ability of the converter to produce the designated output voltages unless the DC voltage dips too low or rises too high for the safe operation of the converter valves. So that is, it is possible to produce the designated sinusoidal output voltage at the wanted single synchronous frequency by appropriately controlling the magnitude of the converter's output voltage. So in this way, the converter can maintain ideal terminal characteristics, that is, the partial sequence synchronous line current would flow through the converter valve, bypassing the DC terminal, and the sub and super synchronous line current components would circulate through the converter valves and the DC capacitor as if the AC terminals were shunted by ideal fundamental frequency voltage sources. So thus, in spite of the modulated DC terminal voltage, the power system would see the TSSC as a perfect synchronous voltage source, so which acts as a short circuit at non-synchronous frequencies. So in other words, from the standpoint of the power system, this TSSC would exhibit AC terminal characteristics identical to those obtained with an ideal converter whose DC terminal voltage is provided by an infinite source of zero impedance. So for converters not having suitable output control capability, an obvious approach to limit the DC bus voltage excursions and the corresponding effects on the DC or AC output voltage is to increase the amount of DC capacitance. So with sufficient DC bus capacitance, the TSSC can produce ideal output voltages irrespective of the compensation of the line current, and it will clearly remain neutral to SSR, that is subsynchronous resonance. So without increasing the DC capacitor size or establishing an internal voltage control capability in the converter, there exists another method of operating the TSSC safely in the presence of subsynchronous line current component. So this approach makes use of the intrinsic ability of the converter to change the phase angle of its output voltages very rapidly. So the technique is best explained using instantaneous vectors to represent the three-phase voltage and current sets. Okay. So by this method, each three-phase set is entirely represented at each instant of time by a single two-dimensional vector. So the vector representing the converter terminal voltages can be controlled in magnitude, that is constant, for example, and as explained previously, can be assigned any angle virtually instantaneously. So by the simple strategy of keeping the converter voltage vector instantaneously and continuously in coordinates with the line current vector, the AC terminal power of the TSSC can be maintained precisely at zero, absolutely irrespective of the nature of the line current. So the DC capacitor thus sees no charging currents during abnormal line conditions, and the DC voltage stays constant. So in view of above general conclusions, consider now the consequences of the prescribed control technique in the presence of SSR on the line. So in this case too, the magnitude of the voltage vector representing the output voltages of the TSSC is freely controlled according to the compensation requirements of the line, but its angle is kept precisely at 90 degrees with respect to the vector representing the three line currents, which are now modulated by the torsional machine oscillations. So thus by definition, the instantaneous total power at the terminals of the TSSC will be maintained at zero. So the TSSC therefore appears in series with the line as an energy neutral device, since at no instant in time does it ever deliver any energy to the network nor absorb any energy from it. So it is evident that an energy neutral device cannot contribute in any way to occurrence of an SSR, which is after all a power oscillation between the generator and various energy storage components. So from the above argument, one can conclude that due to fundamental physical laws, a sufficient condition for the TSSC to remain neutral to subsynchronous oscillations independently of system conditions is to keep its instantaneous output voltage vector in quadrature with the instantaneous line current vector. So by the generality of the above postulated sufficient condition is supported by basic physical laws, it should be recognized that other methods may also be used to exclude the TSSC's active participation in subsynchronous oscillation. So also the TSSC is equipped with a DC power supply, for example, to facilitate real power exchange for resistive line compensation. Then this power supply may also be used to regulate the DC terminal voltage in the presence of subsynchronous line components. So with this, the converter would naturally generate only the desired fundamental compensating voltage and be neutral to subsynchronous resonance. So although not yet proven, it is also very likely that the TSSC, due to the fast, almost instantaneous response of the voltage source converter, can be controlled to be heavily effective in the active damping of freewheeling subsynchronous oscillations brought about by conventional series capacitor compensation. So in discussing dynamic interactions, it is also a consideration that the TSSC, like actively controlled equipment, could under abnormal conditions exhibit instability or oscillatory interaction with the AC system. So for example, if it is a closed loop gains, providing automatic power flow control or other regulative functions are improperly set, or if the economic control itself malfunctions, then however, these considerations are generic to all actively controlled systems and are solvable by the well-established techniques of controllable robustness, control redundancy and production, which are not the subject of this one. Okay, so that's all for today, and in the next class I'm going to discuss remaining topics in this concept. Okay, thank you for watching this video. Okay.